Dear students, now we are going to solve an important expected question for GATE.ESE or public sector undertakings from the topic random variables and random process, and I picked up this beautiful question from our NPTEL workbook from the page 238 and the problem number is 170. Yes, problem number is 170. Now I am going to solve this problem. First of all, we'll try to analyze the problem and then we'll solve. So what is the problem? He said, consider x of t to be white Gaussian noise with zero mean and autocorrelation function eta by 2 into del of tau. Fine. It is passed through an LTI system whose impulse response is h of t is equal to sinc 2wt. Okay, this is the impulse response. What is the power of the output random process y of t? Right. In order to solve this problem, what concepts you must know? Lot of concepts you must know from communication as well as signals and systems also. Right. Now every concept I'll explain and we'll try to solve this problem. What is the first concept? First concept is like this. Passing of what? Random process. Passing of random process through an LTI system. Through an LTI system. Alright. Now observe here. Suppose if I have a random process x of t, input random process I am going to call. If I am going to pass this through a LTI system with impulse response h of t, I am going to get the output random process y of t. See, in this concept you must remember two things. Expectation of y of t is nothing but expectation of x of t multiplied with h of 0. H of 0. So this is the zero frequency response. Zero frequency response. Right? Now expectation of y of t is expectation of x of t multiplied with h of capital H of 0. And the next thing which is useful for our problem is, you must remember this one. How to calculate the output power spectral density. Remember, output power spectral density is nothing but input power spectral density multiplied with magnitude of h of f whole square. This is the second expression, and using this expression only we are going to solve our problem. So I'll do one thing. First of all, I'll put this one in a box, and this can be stated in the other way also. Output power spectral density is equal to input power spectral density into magnitude of h of f whole square, where h of f is the frequency response. How to get the frequency response from the impulse response? Fourier transform of impulse response gives frequency response. Remember, impulse response and frequency response, they form a Fourier transform pair. Here impulse response is given, no? So if I calculate the Fourier transform, I'll get the frequency response. So anyway, you can get this one. Now input autocorrelation function he has given. So if you observe in our problem, input autocorrelation function he gave. Rx of tau is what? Eta by 2 into del of tau, I think he said. Eta by 2 into del of tau. Right. Now, can you find out input power spectral density? Yes. What is the relationship between autocorrelation function and power spectral density? They form a Fourier transform pair. See, autocorrelation function and power spectral density Sx of f, they form a Fourier transform pair. Or I can say that Fourier transform of autocorrelation gives power spectral density, or inverse Fourier transform of power spectral density gives autocorrelation function. So Sx of f, that is input power spectral density, is nothing but Fourier transform of the input autocorrelation function, which will come like this. This is eta by 2. What is the Fourier transform of del of tau? Means impulse signal. See, we know that del of t or del of tau forms a Fourier transform pair with 1, no? Yes. Fine. So this is Fourier transform del of tau is 1. So that input power spectral density I got. So we'll do one thing. Let us capture this one in a box. Right. So if you observe again our expression, see, I want to calculate output power spectral density. Why I want to calculate output power spectral density? He's asking us to calculate the output power. Or if I can calculate the output power spectral density, and if I calculate the area under output power spectral density, that simply gives me power. So input power spectral density obtained, magnitude of h of f. So h of t is given. From this h of t, we must get h of f. How to get? In two ways I'll tell you. Alright. So h of t. What is h of t given? Let us divide our page like this and we'll solve here so that you don't have any confusion. Now what is h of t given? Sinc of 2wt. I'll do one thing. I'll change it to tau for my convenience. Yes, I can change independent variable t or tau. Doesn't make any difference. 2w tau. Right. Now, what is the Fourier transform? What is the Fourier transform of this h of t or h of tau? First of all, in time domain, how does this look like? I told you, using two ways, I'll tell you how to calculate the Fourier transform of this one. The first way is the conceptual way I'm saying. Now, how does this look like in time domain? Sinc pulse means it is like this in time domain. Unlimited in time. Unlimited in time means existing from minus infinite to plus infinite. And remember, in frequency domain, if a signal is unlimited in time, definitely it must be limited in frequency. And the Fourier transform of sinc will be a rectangular pulse. Rectangular pulse. Right? Now, here what are the, look at, what are these points? So if I call this as tau, this is my h of tau. This will be h of f. Right. Now, what is this point? What is this point? What is this point? I want to find out. How to find out? Sinc means what? Sinc of t, if you remember, is nothing but sin pi t by pi t. Sin pi t upon pi t is nothing but sinc of t. In the same way, sinc of 2w tau is nothing but sine of pi times of 2w tau by pi times of 2w tau. In order to get this first null point or zero crossings, equate this numerator to 0, because if sine becomes 0, then only this sinc will become 0. So what I must do? Pi into 2w tau must be equated to plus or minus n pi. Pi gets cancelled, or tau is equal to what will happen? Plus or minus n by 2w. So here observe, this is the first null, no? This will be 1 by 2w. N is equal to 1. This is 2 by 2w minus 1 by 2w minus 2 by 2w, like this. Yes or no? And see, if you want to have the value at 0, the value at 0, okay, we'll calculate first of all value at 0. If you want, substitute tau is equal to 0. Substitute tau is equal to 0. So tau is equal to 0 means what will happen? 0 by 0 will form will come. 0 by 0 form. Yes or no? If I substitute, so you can use L'Hopital rule. L'Hopital rule means differentiate numerator and denominator separately with respect to tau, and then substitute tau is equal to 0. What happens if I differentiate numerator? Cos of pi into 2w tau into pi times 2w by denominator with respect to tau, pi 2w. So this gets cancelled. Now substitute tau is equal to 0. This will be 1. Right? Now always remember the first null point here. The first null point in this sinc is equal to this width. Is equal to reciprocal of this width. Sorry. The first null point here. The first null point here is equal to reciprocal of this width. So this is 1 by 2w means this will be, this width must be 2w. 2w means minus W to W. Minus W to W. Right? Now, what is this value? What is this value? So this is what, now in order to get this value, observe here, value at f is equal to 0 in frequency domain must be equal to area in time domain. From the properties of Fourier transform, value at f is equal to 0 in frequency domain must be equal to area in time domain. So it must be equal to area under the sink 2W tau. Remember, sink T if I take, its area is 1. Sink T or sink tau, if I take, its area is 1. Now what I want area of what? 2W tau. 2W tau, it will be simply 1 by 2W. 1 by 2W. If a signal x of t is having area A, x of alpha t will be having the area is A by mod alpha basically. So sink T area, sink T or tau area is 1, sink 2W tau area would be 1 by 2W. So this height will be 1 by 2W. Wow. I got h of f. Now I can calculate magnitude of h of f whole square. No. Yes, easily I can calculate. Now if that is h of f, what could be magnitude of h of f whole square? That rectangular pulse multiplied with the same rectangular pulse means minus W to W. So 1 by 4W square. Yes or no? 1 by 4W square, because height is here 1 by 2W. If I multiply one more time, 1 by 4W square. For this is my magnitude of h of f whole square, isn't it? Now for this one, an input random process with power spectral density of eta by 2 is passed. Now, can you calculate the output power spectral density? I told you that will try to get h of f by other method, no? Yes, I'll show you within a short while after solving this. After getting the answer, I'll show you. Okay. Now, what is your output power spectral density? Input power spectral density multiplied with magnitude of h of f whole square. But see, this eta by 2 means what? This is existing from minus infinite to plus infinite. But this one is existing from minus W to W, but with a value of 1 by 4W square. So what happens if I multiply? I'll get eta by 2 into 1 by 4W square, but between minus W to W. Do you agree with this one? Yes. Now I got the output power spectral density. Now from the output power spectral density, how to get the output power? Area. Area under power spectral density gives power. So output power is nothing but area means integration from what value to what value? Minus W to W, eta by 2 into 1 by 4W square df. Now we don't have any terms with respect to df, so this will become constant, or eta by 8W square. Integral of df will be f, between minus W to W it will be 2W. Or output power will be eta by 4W. So in this way we are going to get the answer, and we'll see whether we have this answer in the option or not. Yes, option C is the answer. Very good. Yes. Now, what is the other way of getting this h of f? H of f. See, from the Fourier transform, if I have a rectangular pulse varying from minus t by 2 to t by 2 of amplitude A, its Fourier transform is AT sinc of ft. AT sinc of ft. AT sinc of ft. Hope you remember this one. Now I'll do one thing. Instead of t, I'll take tau. Now apply duality property. So duality says that, see, what does the duality property say? Duality property says that if the signal x of t forms a Fourier transform pair with x of f, now if you want to apply duality, bring this here, bring this here. If you bring here, replace f with t. When you bring here, replace t with minus f, so that capital X of t forms a Fourier transform pair with small x of minus f. So what will happen? Bring this here, bring this here. Replace f with t or tau. AT sinc of tau. Now when f or tau with minus f. Replace tau with minus f means replace tau by f and take the reversal. So replace tau by f first. Replace tau by f. And take the reversal. This being an even signal, if I take the reversal, I'll get the same, no? I'll get the same. Now, observe here. So the Fourier transform of AT sinc of tau t will be this one. But what is the impulse response he gave? Sinc of 2w tau he gave. Now comparing, what is there in place of A? 1. What is there in place of t? Look here, what is there in place of t? In the place of t, 1 by 2w. In the place of t, 1 by 2w. Here, if you observe, in the place of t, so in the place of t, not 1 by 2w, it will be 2w. Let me correct that. Yeah. In the place of t, you have 2w, right? Now, here if you observe, this Fourier transform would be this Fourier transform. Here t is not there, so t will come here. 1 by t it will become. See here, t sinc of t, AT sinc of tau t. Here a is anyway 1, but t is not there now here. So here I must, here what happens when t comes here? 1 by t. T is 2w, 1 by t will be 1 by 2w. Minus t by 2 to t by 2 means t is 2w minus w to w. See, so this is your h of t and this becomes your h of f. H of f. Same thing I got. Yes or no? So either way you can follow, I mean whichever is comfortable to you. So in this way we are going to solve this beautiful question in this manner, and you can find these kind of questions, good questions, in our NPTEL workbook. Please refer the workbook.